Hello again, everyone. Here is an example of non-constant current distribution in a wire. I have the current shown in this circle as coming out of the page, and try to use just different size circles to show that the current is more dense towards the outer edge of the wire. All right. We are going to look for the strength of the magnetic field inside of there at this distance r away. So if the current's coming out of the page, we have the field going counterclockwise. All right, so blue is the field. And this is where it gets a little challenging. Since we need to find the charge enclosed within that Amperian loop, we will be given a function for how the current changes. All right, so for this one, the current density, which is J, right, is going to be given by a constant times r squared. So as we move farther out in that wire, the current density increases as a squared function. All right. Okay. We also know that the current density definition is the total current per the total area, which means that the current enclosed divided by the differential area of the loop will equal that charge density. Now, say differential area. It's just a very small section of the, basically a slice of that cross section. It's almost like if you're going to core it. Let's see if I can get this drawn on this paper. All right, so let's get our, let's get a different color here. We'll use this pink. All right, so we're going to pick our Amperian loop, and our Amperian loop is going to go along the field in the same direction, but we're going to have to, let's make that solid. This Amperian loop has got to be a slice. All right, and we're just going to look at the amount of current that's going through that little slice. So when we're close, we have a real little slice. As we move farther and farther away, whatever's contained in those little slices there that have a thickness dr, all right, basically like a small change in the radius. It's a very small change. As we move further and further away, how much current is through each of those slices is going to increase. All right, so let's figure out the charge enclosed from this situation. So I enclosed has to equal the current density, so it has to equal this times this. And we would have to add up all of those loops, all those little sections down here out to R. The current density does change as a function of R, so we're going to replace J with the constant times R squared. And here we're going to have the dA of the loop. Now that little area there is going to be equal to, if we cut that and rolled that out, we would have a length here of 2 pi r at any radius times this thickness dr. All right. So that area is going to be the length, which is 2 pi r, dr. All right, now we have to integrate that. So we're going to combine the like terms. So we're going to have 2 pi c times r cubed dr. So since 2 pi and c are all constants, we're just going to integrate that part. And you can see that we get 2 pi c over 4 r to the 4th. And this will be going from 0 to r. I know it's a little bit redundant using the same variables here, but that would be evaluated from 0 to r, plug r into r, ends up being the same thing. All right? So that'll be the total current enclosed. So that's the tough part. Didn't even start using Amperes Law yet. Just the idea of current density and integrating out until we get to that desired distance away from the center. All right, let me try to move that away. Just enough so we can see the eye enclosed. All right, let's start with Amperes Law. Closed loop integral of v dot ds. Going to be 1 anyway. Mu naught I enclosed. All right, looking for b. The still length of our Amperean loop is still 2 pi r equals mu naught. Now we have our I enclosed. You can see 2 pi c over 4 times r to the 4th. And just simplify that up there, all right? This 2 cancels out that 2, this pi cancels out that pi, this r cancels out one of those r's. And we get our final answer. B is equal to u naught c over 4 times r cubed. All right. So as we move farther away from the center, our magnetic field increases by a power of 3. We should be able to do that with any function they give us. We could have the current more dense towards the center and then end up weaker out there. It would just be an inverse relationship, and we just got to make sure we can do this setup right here for whatever function they give us as the non-uniform charge density, or current distribution density. All right, so that's it for Amperes Law. If I can get another one of the non-uniform examples together, I will, or maybe we'll just get one done in class.